Hello and welcome to this first video where we're actually doing something, right? In the actual first video, I presented you the project and the prerequisites that you should at least have a bit of a knowledge on, so you can continue in this course without having any sorts of issues. And in this lecture, as I said, we're actually going to do something. And to get started with, we're going to create our project. So I already have Unity open here. As you can see, I'm using 5.1. But you should be good with any of the 5.x versions. So to get started, I'm gonna hit new project here because we're gonna start a project from scratch. I'm gonna choose 2D because this is going to be a 2D project. It's gonna be a 2D game. You can just choose a location where you can save your project at, and just choose a good name, a meaningful name. I'm gonna name mine Wood Breaker game. Just hit create project and we're good to go. So as per the title of this video, we're just going to be bringing the stuff that we're going to be using, and for that I mean sprites and UI elements that we might be using throughout this course. So I'm just going to bring mine here on project. I'm going to select project here, and I'm going to bring my assets into the project. I already have them open here, so there's a folder named sprites. There are two subfolders. One is game, where we have the actual sprites of the game, and there's one named UI, where we have the UI elements. So I'm just gonna bring both of these, drag them and drop inside the assets folder. There you go, it's already been imported. Let's just check that everything is marked to be 2D or UI, because this is a game that basically uses sprites and UI elements. So I'm gonna go inside my sprites folder, inside games folder, and if I click in one of these, they are already set to the texture type 2D and UI. So in case they're not, just go ahead and change the type to sprite and then click apply. And let's just check my UI elements. They're also marked to be 2D and UI sprites, okay? So what we'll be doing in this particular lesson is just creating a few prefabs that we'll be using along the way. Something that you might notice is that my viewport, my layout is not set up as yours probably is. So if you want yours to be the same as mine, you can just choose the default layout, and this is probably what you have because this is the default layout of Unity. And you just click on game tab here and you bring it to the right, and there you go, that's set up. Okay, so as I said earlier, we're just going to be setting up some prefabs that we must have to use later in this project. And actually, the only prefabs that we need, because they're going to be instantiated in our game in real time, are the wood plank sprites. Because the apple is something that's already that's going to be in our game from the beginning to the end. So it's something that we can just place in the scene right away. The leaves bush, the same thing. But the wood planks, we have to create them dynamically. So the best thing we can do is just to create prefabs from them, and then we can use them afterwards, okay? So I'm gonna be bringing one of these to my scene. Just click in one of these, drag it and drop on your scene, and there you go. It's a bit too big, as you can see in our game view. I'm gonna be bringing them down a little bit in terms of scale. So I'm gonna scale them down maybe to 0.1. So they're just too big. I'm gonna round this down to 0.1. And they're also gonna have a collider because as you've seen in the project preview, this game is basically about moving this apple around, actually not directly, but indirectly moving this apple around and make it hit these wood planks. So in order for this item to receive collision, it must have a collider, okay? So to add a collider on this element, you just go to Component, Physics 2D, and then Box Collider 2D. There are a few other options, but I'm going to choose Box Collider because this is basically a rectangle, which can be very precisely represented by a box collider. So if you click on these, there is a collider that wraps up our element very nicely, okay? So this should be good. And to create a prefab out of these, I'm just going to create a new folder here. I'm going to click on Assets here, right click, Create Folder. I'm going to name my folder Prefabs. And inside this folder, I'm going to just drag and drop my game object here. And as you can see, it now has name turned to blue, which means this is an instance of a prefab. And in this case, it is an instance of this prefab right here. I can now just drag and drop this prefab as many times as I want. The scale is already set to 0.1 as we want. And they also have this box collider, so they're all set up. We just have 3 more variations of this wood plank, as you can see inside my game folder, inside the sprites folder. There are 2 more variations, the wood plank 1 and the wood plank 3. So to add these as prefabs, you don't have to drag them here, scale them down to 0.1 and then add a collider. What you can do is just choose this same prefab that we already have because it's all set up, but we just have to change the sprite to be something else. So I just click this little circle button here, and then I can choose another sprite, in this case the wood plank 2. There you go, but we can just hit apply to apply these changes to the existing prefab because it's going to overwrite all the things that we did in this wood plank 1 prefab. What we can do is just change the name of this element, so I'm going to change it to wood plank 2, and I can just drag it and drop inside my prefabs folder, so I can make a prefab out of this element. So they're independent, they're different, and it's a much easier way to set up your prefabs when they just have a slight change from one another. And what I can do for the third element is just to select this one, change the name to wood plank 3, so we don't get naming issues. Change the sprite to be the wood plank 3, and drag it and drop inside my prefabs folder, and they are all set up, okay? So I'm just gonna remove this element here, right click, delete, and maybe I can start to set up my elements here. I can just put the scenario here, so I'm gonna go under the game folder, drag the scenario here. I'm gonna zero out the position, so on X I'm gonna make it 0, same as Y. I'm gonna scale it down a little bit, it's kinda too big. Okay, so this looks good. Actually, instead of scaling my element down, I can just click on my main camera and you can see it's set to orthographic because I set my game to be 2D. In case you missed this step and you set your game to be 3D, you're gonna have to go in your camera and change it from perspective to orthographic. Okay, and other than that, you're gonna have to choose this 2D option right here. Okay, so since my camera is orthographic, I can just change the size, and this is going to change the volume that it's actually rendering, and from that we're gonna render a much bigger area, so we can scale our elements this way as well. I'm gonna leave it as being 5. That's what it was, because this scale is good enough. I'm just gonna bring my leaves brush here because this is our actual player and is enormous, so I'm gonna bring the scale down to maybe 0.1. No, that's too small. Maybe 0.1 is good. Let's try changing the y-axis. No, that's much smaller than I thought. 0.2 looks good. On the Z we can just make it 1 or 0.2, it doesn't really matter because there's no such thing as a z dimension here because we're dealing with 2D, okay? So I'm just gonna click on this move tool, move it down a little bit. I'm gonna zero out the X position so it's basically centered. And there's an issue here. It's actually not an issue, but it's something that might bring us problems in the future. As you can see, the scenario has its order in layer as 1. Our leaves bush also has the order in layer as 1. So they're actually overlapping each other. You can see this, but they are. What we can do is set the order in layer of the leaves bush to be 1 just to render it after the scenario. So a higher value means render it after, a lower value means render it before. So in case I put the leaves bush to render before the scenario, which has the order 0, in case I put -1 here, you can see that the leaves bush gets rendered before the scenario, but what we want is the inverse. So I'm just going to make the leaves bush with an order of 1. I'm going to also bring down the apple here. It's also huge, so I'm going to scale it down to 0.2. That's too big, maybe 0.1 will do. That's also huge, maybe 0.05. This looks good. So I'm also going to zero out all of its positions, move it down a little bit, and change the order to be 1. Since the apple and the leaves bush will never overlap each other, we don't have to care about the order and layer of those, because we're going to have colliders for them. So every time the apple hits the collider of the leaves bush, it's going to reflect its movement. So they're never going to overlap each other, and this is not a problem. Well, for now, this is all we need, because in the next lecture, we're going to move our platform around. The apple will stand still for a little bit, because we have to deal with first things first. But I guess this is it for this video. Okay, since we gotta start somewhere, let's start by moving our platform. We have this leaves bush here, and that's basically our player, because we're going to be able to move this, let's say, character to the left and to the right, because the apple is going to move towards the ground, and we got to catch it. We can't let the apple fall to the ground. This is the basic rule of the game. So I'm just going to explain a little bit about moving something around and how we do it. So we can get this right in our head and can apply this to other stuff. So I'm just gonna open up my drawing app here, and this is our basic structure. As you can see, this is my bush here, and there's a Y component that points upwards, and there's an X component that points to the right. Of course, we gotta receive input from somewhere. So we have basically two options. We can receive input from the mouse. So moving the mouse to the left means we're going to move the bush to the left, and so on. We can also receive input from keyboards. So we can maybe use A and D, or maybe left and right key. So for simplicity, let's say that this is our system here. So how do we move something in programming or in game development? How do we move something? To move something, we basically need to add a contribution to that object's position. So let's say we have a ball here. This ball is placed at let's say a position 0, 0. So if I want to move it to the right, and basically moving to the right has, of course, a vector that points to the right, and that vector is 1, 0. That's 1 for X and 0 for Y. So if I want to move this ball to the right, that means I have to get the position of the ball and increase it by a vector that points to the right. So basically by doing, let's say, b.pos, it's going to receive itself. plus C, which is a contribution. So in the other frame, in the next frame, the ball is going to be in this position, which is now 1, 0, because I summed the current position to the contribution, and that gives us 1 and 0. In case I do this again, and I sum the current position to the contribution, my ball is going to be in the vector 2, 1, because we sum component by component, and this is how we got our answer, okay? And this is basically how our platform is going to work. If you notice here, I already pointed out a vector that's called vector3.write, and this is basically short for writing 1, 0, 0. So 1 for x, 0 for y, and 0 for z, which means that this vector is going to point directly to the right. So if I get the platform, if I get its position, which is currently here, and if I move it by this vector, multiply it by the amount of movement I want to add, I can end up here or here, because it depends on my input. Basically, if I got a positive input, which means that I want to move to the right, I'm going to have a vector that points this way. If I got an input that goes to the left, that means I'm going to multiply this vector by -1. And that, in short terms, mean that I'm going to inverse its direction. So it's going to end up pointing this way. So depending on the input, the direction of my movement is going to change. And I pointed out here that moving the mouse to the left is going to cause a -1. Moving it to the right is going to cause a 1. So this is for the direction of the movement. The same happens for the A and D keyboards. Alright, so now how do we code this? First of all, I'm going to create a folder, and I'm going to call it scripts. This is where we're going to place every script that we possibly write. And I'm going to create a new one. I'm going to call it platform. Double click to open it. While it's opening, I'm just going to show you something very quick. As I said to you, we need to have access to the position. We need both access to writing to the position and to reading from the position, because we need to use the position to add a contribution and then place the position again as the current position of our platform. So if you click on the leaves brush here, I move it slightly to the right. So I'm just going to reset its position. As you can see, I'm changing the position under the transform component. So by doing this via script, we need to access the transform component and then access the position. This is how we do pretty much anything in scripting in terms of changing some object's behavior. We have to access a component, and from that we can change a variable that's stored inside of this component. In this case, we want to access the transform component and change the position that is, of course, an attribute of the transform component. So to do this programmatically, let's say we want to do this in the update function, which means that we are doing this at every frame. To get access to the transform component, we need to do get component, and then in between minus and plus signs, we place the component that we actually want to have access to, which is transform with an uppercase T, and put your parentheses here. This function has no attributes, no parameters, just a semicolon here, meaning that this is a comment. So this comment or statement is going to return us an instance of the component transform. So we gotta store it somewhere, right? So I'm just gonna store it on a transform local variable. I'm gonna call it T. So basically T has a reference to that component, has a reference to the transform component where this script is going to be attached to. So now if I do, for instance, t.position receives t.position plus some contribution, let's say vector3.write, whenever I place this script onto any object, it's going to start moving to the right immediately. Okay, so let's try this out. if I add this script to our platform and if I hit play, it's gone. And you can see the position increasing by 1 at every frame. But how do we get this, this input? We're gonna get it through what's called an axis. So from the name, maybe you can derive what it does. An axis is something that has a value that varies in one direction. So for instance, the axis for a mouse input is going to vary between -1 and 1 depending on the direction of the mouse movement. And of course, I mean the mouse X component. The mouse Y component works the same way, but we're talking about the X component because it's a logical thing. We want to move the mouse to the left or to the right to move the platform to that same direction. If you want to have access to the axis that Unity already has, you can click on Edit, Project Settings, and Input. So you can expand the axis here, and here are the axes that you already have. So there's a mouse X one here. That's basically going to give you this behavior that I pointed out here. It's going to give you -1 when it's moving to the left. It's going to give you 1 when it's moving to the right. It's going to give you 0 when it's not moving on the x-axis. And it's going to give you something in between if you're moving at a slower speed. So let's try this out. Let's try to get this value. So of course it returns a float because it's something that varies between -1 and 1. I'm going to store it in a float variable. So I'm going to call it mouse x movement. This is going to be the result of that axis, whatever value that axis is being right now. So to get access to that, we need to go to the class input, which is of course the class that handles any sorts of inputs, that being keyboard, mouse, anything like that. And then we type get axis, which is the function that will return as the value for a axis that we define. In our case, we want to type mouse x here, because as you can see, let's go back to Unity, they have a name, and this is the name that we need to pass in to retrieve the value. So any of these axes, they have a specific name, and you need to pass that as a string to get its value. So in this case, what we need to do is just to multiply the right direction by this mouse X movement, and then we get a working behavior. If you go back to Unity and if you hit play, you can see that by moving the mouse to the left and to the right, I get the corresponding effect on the platform, okay? Of course, we can add a velocity so we can control it better. So I'm going to expose a public float, which is going to be the velocity. And I can just, of course, multiply this value by the velocity. So a smaller value for the velocity is going to bring me, it's going to give me a smaller contribution to the position, which is going to make my brush move slower, okay? Going back to Unity, if I select the leaves brush, which is where the script's attached to, I have this velocity variable here, and setting it to maybe 0.1 gives me the motion that I want. Let's think of something here. This function update runs at every frame. Let's say that you run this game in a faster computer. What that implies? It implies that the update function is going to be called more times per second because that computer has more power and therefore is going to bring the FPS to a higher value. If you run it in a slower computer, the update function is going to be called less times, which means that if I call this line more times per second, it means that I'm going to move my object at a higher speed. If I call this line less times per second, it means that I'm going to move my object at a slower speed. And this is a problem because, especially if you have games that are multiplayer, you don't want to have a player that runs faster than the other just because that player is running in the game in a much better computer, right? So you have a special variable that scales the time based on the velocity of that computer, and that variable can be accessed in time.delta time. So this is the variable. It basically tells you how many seconds it took the computer to render the last frame. And what this is going to do the following. So let's say that I got an FPS, which means frame per second, and I'm going to put an age here, which means that's for a better computer. And I'm also going to multiply that by the time it took it to render the last frame. So I'm going to say delta time sub h. This has to be equal to FPS dot L, which is sub L, which is basically the FPS for a slower computer, times delta time sub L, which is the delta time for a slower computer. And why is that true? Because when the FPS increases, the delta time decreases. Because if your FPS is higher, it means that every frame takes less time to compute, so this variable is going to drop down. In this case, as the FPS goes down, the time it takes to render a single frame goes up. So this equation holds and makes such a fact that depending on the computer, a player cannot run faster than the other. This is a very powerful effect that sometimes is not explained well, and you got that thinking, oh, I don't understand this, I'm just going to type in because someone told me. So this is what's actually going on. And just before we get done with this lecture, of course, since time.delta time is a very small value, we now have to increase the velocity to a large value in order to get a good movement. Okay, so I'm going to increase it by 20. 20 seems to be too much. Maybe 5. And 5 seems to be a good value. And what you can also notice is that I can move my platform off screen, but you can see it has a limit. When I get here, it means that's the limit. And by the transform, you can see that position is 3.4 roughly. So what I'm going to do is I'm going to clamp the position in the x-axis between a limit that I define. So to correct that, what I'm going to do is I'm going to expose a variable here, which is going to be the limit on x. So first of all, we need to get access to the axis that we want to clamp. In this case, is the x-axis. So I'm just going to put the x-axis on a variable that's a float. I'm going to call it current x, and this is equal to t.position.x, basically the x value of this transform currently. And to clamp this value, I basically want to say that this position needs to be between minus limit on x and plus limit on x. It has to be clamped in between those values. Why? Because I know that my character, my platform, is aligned in the x-axis. It means that it starts out at 0, so it needs to be in between those values. So to clamp this current x, I basically have to call a function that's going to make this adjustment. So I can say current x is equal to mathf, which is the class for mathematical functions, dot clamp, and this is going to clamp a value in between min and max. The value that I want to clamp is current x. The minimum value is minus limit on x, and the maximum value is plus limit on x. But now I just have the value clamped. I need to reattach it to my position. And to do that, I need to assign a new vector to the position. So t.position is equal to a new vector. The x has been changed, so I need to pass in the new x, which is current x. The y doesn't change, right? So I'm just going to pass in t.position.y, which is the current value for y. Since it doesn't change, I can just pass the current value. The same happens for z. Okay, so this is going to clamp the platform so it doesn't go off screen, given that we provided the correct value for limit on x. So going back to Unity, now we have this limit on x, and you can see that it goes off screen when it gets higher than 3.4, let's say. So I'm going to put the limit on x being 3.4. It's going to zero out this x-axis When I hit play, you can see that it doesn't go off screen. Once it gets smaller than minus 3.4, it gets the value minus 3.4, and once it tries to get higher than 3.4, it receives the value 3.4. So this is what clamping does. Alright, so this is it for this video. In the next one, we're going to move our platform using keyboard inputs. So now for the movement via keyboards. This is going to be a relatively easy step, given that we already know how to move something. So we just need to define an axis that's going to move left or right depending on the keys we press. So going back to Unity, I'm going to go into Edit, Project Settings, and Input. It's already expanded. So notice that you have this horizontal axis, and the negative button for that is left, the left arrow key, and the positive button is the right. What is a negative and a positive button? A negative button is something that when pressed is going to give you a negative value, and the positive button when pressed is going to give you a positive button. So this is what defines an axis, okay? So you can use this horizontal axis, or maybe you can define your own. Let's define our own. I'm going to expand the size to 19 so we don't lose any of the Unity's predefined inputs. And there's another cancel one, which is, the last one gets duplicated. I'm going to expand it, change its name to maybe our arrow input. And then for negative button, we can press A, hit enter, and positive button, we can press D, hit enter. Okay, so now we just have to grab the value of this input, and it's going to be a negative value when we press A, it's going to be positive when we press D. Very simple. So going back to our script here, we just have to grab this input as I told earlier. So let's attach it to a floating point value. I'm gonna give a name that can be keys movement, and this is going to be whatever value is retrieved by input.getAxis, and the axis I want to get is what's the name that I gave? Gosh, or input, or arrow input. Okay, so now it's a very tricky thing, because we can't just multiply by this position, because if we do so, what's going to happen is that when we press D and move the mouse to the right, let's say, we're going to move twice as fast, and that's cheating, of course. So we need to verify when just one of these elements is different than 0, and then we can move our platform. So when both of these are different than 0, that means that both of these are receiving inputs, and that's cheating, so we want to avoid that. We can check if mouse X movement is different than 0. Then we can add this line of code, which is going to make the object move to the left or to the right depending on mouse input. And we can add an else if, so we can check for another condition. Let's just check for the keys movement here. And then we can of course just copy and paste this line, but instead of writing mouse X movement, which we know that is 0, if we get to this else if, it means that mouse X needs to be 0. So instead of multiplying by mouse X movement, we multiply by keys movement. Of course, we need to verify if this is different than 0, which means that there's any input going on. Okay, so this is what we're going to do, and notice that we're clamping regardless of key movement or mouse movement. So this is going to happen, as said, regardless of any movement that happened. Even if no movement happened, we're going to clamp anyways. That's of course waste of processing, but in this case it doesn't really matter because it's a simple game. Okay, so once we go back to Unity, we can either move by keyboard and by mouse, but when we try to move in the same way with mouse and keyboard, it doesn't go twice as fast. And this is it. Okay, so moving on in our videos, before we actually code the apple, because the apple is something that moves in a diagonal direction and is sometimes actually it will obviously hit one of the corners of the screen, we actually need to code the screen borders, right? We need to define where are the places that when the apple hits those corners, it will change its direction. It's basically reflect its direction. Okay, so this is not an issue for this lecture, but I just need to expose why we need to do this first before we code the actual movement of the apple. I'd also like to apologize for my voice. I catch a cold, so it's a little bit different, which is of course not an issue for our series. So let's continue. Also, one more comment before we move on. Don't forget to save your scene. Just click File, Save Scene. It will pop up a little window that's gonna ask you for a place to save it inside the assets folder and a name for your scene. As you can see, I've already saved mine. Is this game scene here? It has this Unity icon, so this is a scene, and you just double click it and it's gonna open the scene for you. So after every single lecture we do, I'll ask you to save the scene. When I don't, do it anyways because I might forget. So what were we gonna use to define the borders of our game? I'm gonna create a new empty game object, going to game object, create empty, and I'm gonna name this object screen collider. And to this game object, I'm going to add a component, which is actually a collider, but it's a specific type of collider that we didn't see yet. We're going to go to component, physics 2D, and we're going to choose one of these 4 colliders, and we're going to go for the edge collider. And what does the edge collider do? If you pay attention, it has this green line here, and this is an edge of the collision. So every time one of the 2D colliders that we have in our scene hit this edge here, it's gonna collide with it. So this is basically something that we can define, and to edit this collider that's gonna wrap our scene, we can just click on this icon here, and we can click on one of these corners and we can pull it. If you want to add another point, you just click at any place here and drag it out or drag it in. Now you have 3 points. Just drag another one so we can wrap our scenario. But as you can see, it's very hard to encapsulate our screen with this, especially when our screen changes its size. As you can see, we have an aspect for our game, and this varies according to the device where you're playing the game. So if you're playing on an iPad, of course the dimensions of the screen are going to be different, therefore the aspect ratio will be different. The same applies for an iPhone or maybe an Android device or maybe any computer that you might have. So if you choose a different aspect ratio, for instance this one, it'll have another appearance, or this one. So you can see that the aspect ratio changes the dimensions, and of course this collider we've just defined is not going to apply for every dimension that we might have, so we need to create it dynamically. You can check this option gizmos here, so it's going to show where the actual collider is on the screen. It's kind of hard to see, but there's a green line here that is going to actually show where the collider is. So if I move this point here, it's going to move that edge on the screen. It's just a way that we can see the gizmos. This is a gizmo. This is something that is drawn, but it's not supposed to be presented on the game view. But if we choose this option, gizmos, we're gonna allow this thing to be rendered on the game scene, basically for debugging. So doing this, we can see that the collider gets shown here on the game view. So what are we going to do? In this edge collider component, you see that there's a points thing that you can expand here. And this is basically the set of points that are going to make this edge collider. So for each 2 points, you get an edge. So this is 1. This is 1. So for these 2, you get an edge. For this one and this one, you get another edge. For this one and this one, you get another edge. And for this one and this one, you get another edge. So as you can see, there are 5 points to represent 4 edges. And what we basically have to do, we need to assign these points dynamically through scripting. So what we need to do is to check where the corners of the screen are in world coordinates, which is these coordinates that are represented in the scene. So here I have a little draw that shows me the world view and the screen view. The world view is something that is 3D, and the screen view is something that is 2D. It's basically the pixels of our screen. So let's say that our screen starts in this bottom corner here, and this is the pixel 0, 0. And it goes all the way up to this one, which is the pixel, let's say that is 1280 by 720. This is HD, okay? We have 1280 width and 720 height, okay? So what we want to do is basically to get all of these 4 corners, what will this one be? So as you can see, the width for this point is 0 because we didn't move along the x-axis, so it's 0, but the height is 720. In this case, the width is 1280 because we move all the way to the end of the x-axis, but the height is 0 because we didn't move along the y-axis. So what we need to do is basically we need to grab those pixels, we need to grab these things that are in screen view, in screen coordinates, and we need to get their correspondent position in 3D. So we need to basically do this conversion from screen view to world view. So let's say that we have a ball here, that's a 3D thing. And let's say that this ball's position is in the world coordinates is 0 in x, 20 in the y-axis, and 3.4 on the z-axis. When the game renders this ball into the screen view, it gets, let's say, it gets placed here. So this is the ball. It's actually in 2D. And the screen coordinates for this are going to be, let's say, 1000 by 680. So as you can see, when I converted this thing that is in world view to the screen view, it gets this position here. But if I do the opposite, if I convert this position, which is 1780, to the 3D view, to the world view, it's gonna get this position here. So I want to do this same thing, but instead of doing it for an object or anything like that, I want to do it fixed coordinates, which are the four corners of my screen. So I'm basically gonna connect this corner. So this is gonna form an edge. I'm gonna connect these 2 corners. I'm gonna connect these 2, and I'm gonna connect these 2, and they're gonna form our collider. But how do we actually go on and code this? It's very simple. First of all, I'm gonna create a new script, and I'm gonna name it Collider Creator. Double click to open it up. So one thing that we must know is that all these transformations that go from 2D to 3D, from screen view to world view, they are done through the camera component. So we need to have a reference for the camera. So let's put a public camera reference to a camera, of course, camera component, and let's type in cam. We basically have a reference for the camera, and it's called cam. It's a variable that's in our script. And we also need a reference for the edge collider because we want to edit its points. So we can define public edge collider 2D, and this is my collider, okay? So when we convert from 2D to 3D, we're gonna get a vector 3, which is basically a point in space. We're basically gonna call a function that will convert a point from the screen to a point in the world, and as said, this is gonna return a point in space, which is a vector 3. So I'm gonna assign whatever my function returns to a vector 3 type. And I'm gonna start by getting the bottom left corner. So this is the bottom left. And the bottom left is the pixel 0, 0. So I'm going to convert the pixel 0, 0 from my screen to the world. And I do this by saying cam. We're going to access a function of the camera component, which is called screen to world point. And it makes sense, right? I want to convert a point from screen to world. And what is this point in screen? We need to pass a vector 3. And it's 0, 0. This is for x and y. And let's say that the z is worth 0, even though it's not going to be used because we're not dealing with depth here. This is all 2D, so we can easily pass in z as being 0. So we're going to convert a pixel 0, 0 into the world coordinates. We can do the same for, let's say, the upper left. And this is basically just changing the height instead of being 0 to whatever height is our screen view. And how do I dynamically get the height of the game view? I do this by saying, of course, x is going to be 0 because we're dealing with the left corners. So the y is going to be screen.height. And this is going to tell me what the height is for this specific aspect ratio. This is always going to be the height of the resolution that I pick for my game. Now we can move on to the upper right. So the upper right corner is the corner that has x being evaluated at its maximum and the height as well. So we need to pass in the maximum x value for our screen coordinates. So as we did with the height, we can easily do it width. So screen.width, this is our x value. The height keeps being screen.height, and z is worth 0. So now for the last point, this is the bottom right. We don't have any height, so y is going to be 0. But we are at the right of the screen, so x needs to be screen.width. There you go. Now we just need to attach these positions as being the points of the collider. And we can do that by doing collider.points. Make sure you grab your variable and not a component that has a capitalized C. So collider.points. And we need to say that this is going to be a new set of points. So we do new vector2 of 5 elements. As you saw before, we need 5 elements to create 4 edges. And to define what these points are going to be, we need to put curly brackets, and inside here we're going to pass in the 5 elements that's going to compose our vector of points. Note that this is an array of vector 2, but it shouldn't be a problem because there's an implicit conversion between vector 3 and vector 2. So let's pass in our 5 points. Let's start by the bottom left. Now we can go to the upper left, now upper right, and now bottom right. we're doing this in a clockwise direction. And now to finish, we need to pass the first point again as being the last one. So we're gonna wrap our screen with this collider. And this should do it. So let's go back to Unity. Let's attach our collider creator into our screen collider game object. Now we need a reference for the camera. So let's drag our main camera here. And let's also drag the edge collider 2D as being our collider. And when I press play, hopefully we will have something that wraps our game, but not quite. So something happened here. And as you can see, our screen collider has a Y position of -4.6. And this can't happen because, as you can see, when I move the collider and it has its points defined, the points are actually going to be summed up to the actual position of this collider, so it will displace the points. And what we need to do to solve this is basically we need to reset this position. So click on this little gear here, reset, and when I hit play, there you go. It looks like now we have our screen wrapped up with this collider. Okay, and to check if this is working, you can just maybe apply a rigid body to this apple. So let's apply rigid body here. Component, physics 2D, rigid body 2D. And we can also apply a box collider to it so it's not going to fall through. Box collider. And when I hit play, there you go. It doesn't fall through our scenario because it has this collider. And it works perfectly. So I'm going to keep these components in the apple. I'm just going to disable the gravity scale so gravity won't affect this element, and I'm going to quickly save my scene, and this is it for this video. Now let's put our efforts into trying to make this game more dynamic. There's nothing much going on here, of course. There is just we're just generating a collider, and there is just the ability for us to move our platform around. And as you can see, because I changed the aspect ratio, one thing I just noticed is that the limits are wrong. Okay, so this is something that we need to pay attention in the future, because we can generate the limits dynamically as well, using a similar approach as we did for the scenario limits. But we won't deal with this now because it's not something that's really important for the project to work as expected. But instead, we're going to work on the apple movement. We're going to make the apple move in such a way that when it, for instance, hits one of these corners, the movement gets reflected, and then it goes this way, and then it goes this way, and then it goes this way, and so on and so forth. Okay, so this is what we're going to focus on this video. So what we're looking for the movement, we want to start with two directions for the movement, two possible directions. One is going to be the direction going this way, and as you can see, this is a vector that has components 1, 1, or something that goes along this direction. So it can be an alpha value that multiplies this direction. So it can be something that's bigger, it can be something that's smaller, so on and so forth. But it's going, as long as alpha is positive, it's going to be something that lies within this line here. Okay, and the other possible direction is going to be this one, which is of course -1 and 1. So what we're going to do, we're going to randomize a number, and depending on the result we get, we're going to start with this vector or this vector. So let's say that we can generate a floating point value that has its limits between -1 and 1. And then we're going to get, let's say, a value that's minus 0.3 or maybe 0.1, maybe 0. And then we can just use a function that's going to get the sign of this number. And the sign will basically be minus 1 or 1. So this function is going to give minus 1 for this value. It's going to give 1 for this value, and it's going to be 1 for 0 as well. So this is a very simple approach, and we're going to do this right now. So going back to Unity, I'm going to create a new script. I'm going to call it Apple. Double click to open it up on Model Develop so we can start coding this. Alright, so first of all, we need to have a velocity for this movement. So I'm going to define a public floating point value here, which will be the velocity. And to start with, whenever I apply this script to an object, I want this velocity to be 1 as a standard value. So I just say that this is going to be equal 1. So whenever I apply this script to a game object, the velocity will start out being 1. And on the start function, I'm going to define a direction, but I need this direction to be a member of the class, so I can have access to this variable on any function that I may want. So I'm going to define a private vector3 underscore direction. This is a common way to write private members. We just do a underscore in front of the variable. And so we can pick a random direction. We're going to define this float value, and this is a random value. And to get a random value that's between two limits, we can use the function random.range. And this asks for a minimum value and a maximum value. So we're going to basically randomize between min and max. And this has two overloads. It has one that takes integers, and here is a quick description. So returns a random integer number between min inclusive and max exclusive. So if you say the minimum is 1 and the max is 2, it's going to return either -1, 0, or 1. The maximum is not included. But instead we're going to use the floating point approach. So this includes both minimum and maximum. It's going to return a floating point value. And we're going to say -1f, just to make sure that we grab the floating point overload, and 1f. If we take off these f's here, we're going to use that integer overload, which is not something that we're looking for. You can also put a 0.0 here just to make it even clearer that we're using the floating point overload. And now the x component will just be the sign of this floating point value. So mathf, which is the class that holds all sorts of mathematical functions, and inside this function we have these sign operations. So it's going to return the sign of this floating point value. And the floating point value, of course, is the random value. And now for the direction of the movement, we can just assign a new vector to this one. And the x component is, of course, this integer that we've just defined, so x component. The y is always going to be 1, because we always want to move upwards to start with. And the z is going to be 0 because there's no movement on the z component. This is a 2D game. And just so we grab a vector that is normalized, and what does that mean? Is that we want a vector that has size 1. We're going to do direction.normalize. We're going to call a method that is going to normalize this vector here. Note that this is different than direction.normalized. This attribute is going to return the normalized version of this vector. So if we use this approach instead, we would need to assign the normalized vector to the direction again. But if we use this method, direction.normalize, this is going to normalize this vector, and it's not going to return a normalized version. Now we have a normalized vector, and in other words, a normalized vector is basically a vector divided by its length. And what this is going to do, it's going to make such operation that the length of this vector from now on is going to be 1. So Now the size of this vector is going to be defined by the velocity. So if you get the velocity being equal to 1, we get just a normalized vector because anything times 1 is anything. If we multiply it by 2, we get a direction that's twice as big, therefore we get a velocity that's twice as big, so on and so forth. And now what we want to do in the update function is just to grab the position of this element, and we can do get component transform dot position plus equals, that's basically adding to the position. So doing plus equals is just doing equals itself plus the direction times the velocity. I'm just gonna put this into parentheses so we make sure we're first multiplying direction times velocity and then we're adding this to the position. So doing that times equals is the same thing as doing this. We are adding to the position instead of assigning to the position. And this works with minus, with multiplication, it works with division, and all sorts of operations. Also, please note that there's a shortcut for writing get component angle brackets transform. We can use just transform with a lowercase t instead. So transform the position plus equals direction times velocity. This is a shortcut that's not available for any sorts of components, but the transform component is kind of surviving through the versions of Unity. So you can just use this shortcut to access the transform component of the object where this script is attached to. You don't have to write get component transform all the time. And let's see what this is going to do. So we can go back to Unity. And when I hit play, oops, there's an error here. It says cannot implicitly convert type float to integer. And that's because the sign function returns a float, but I'm trying to assign this to an integer. So I can just convert the result of this to an integer, or I can use a float instead. It doesn't really matter. I can just use float x component equal to the sign function, or I can say this is an integer, and I can force the returning value to be an integer by doing parenthesis int in front of this function call. This is going to make such an operation that the returning value is going to be converted into an integer before it gets assigned to this local variable. So both of these solve the problem. Now the error is gone. So when I hit play, first of all, of course, I need to apply this script to the apple. So I'm just gonna click on the component to hide them because my screen is broken and I can't see much. So I'm gonna assign the apple here. There is just a velocity, so we're good with 1 for now. So it goes this way. When I hit play again, it goes the other way. And now we have a randomized initial direction, okay? Of course, we need to multiply the movement by time.delta time. So this movement is not dependent on the frames per second of our application. And now we can increase the velocity to make the movement faster. 10 looks a bit too much, maybe 5. Yeah, that looks good. And you just saw that when I hit the collider here, it tries to get through. Eventually it's gonna go through because I'm forcing it by adding to the position, and this is not something that we should do when we're dealing with physics. But we just want to hit this wall, and then this invisible wall, right? And then we're gonna grab its normal, which you'll learn within a few moments what it is. But we just need to hit this wall and we're gonna reflect the movement direction, okay? So we won't be forcing the position to keep adding to itself, so we won't pass through this invisible wall, okay? But as you can see, the physics is working and we're colliding with that wall. All right, so now how do we reflect such movement? Okay, so let's go back to drawing a little bit. And as you can see, let's say that we start out with a direction of 1 and 1. So we're going to move our apple and eventually it will collide with this wall. Okay, so you gotta note that when you collide with something, you can access a component that's the normal of the element that you just collided with. And the normal is something that it's orthogonal to whatever you collide with. In this case, this edge has a direction vector that points this way, and something that's orthogonal to this one will be something that points down, or maybe up, but in this case it's going to be down. So what we want to do is basically we want to grab this direction, which is something that it's going to be pointing this way, and we want to reflect this vector along the normal that's represented by this sign. And after we do that, we're gonna end up with a direction that points this way. So we basically just reflected the movement, and eventually, of course, we'll be moving down this direction. We're gonna hit this wall. This wall is going to have a normal that points this way because it's orthogonal to the edge. And we're going to reflect, so it's going to be something like this. And we're going to be going down towards this part of our scenario, which of course is a game over, but we'll try to reflect the movement with the platform. But for now, let's just do this reflection thing. So I can open up my script, and for that we need a function that actually detects collision, and Unity has a built-in function for that, which is called onCollisionEnter. And this is just like start and update, which are functions that are called by Unity when something happens, when a special event happens. So to get access to this function, we need to type in void onCollisionEnter 2D, because we basically are dealing with 2D collisions. If you're dealing with 3D collisions, we just need to take off this 2D here. So in this case, it's 2D. And the parameter of this function is collision 2D collider. So what's going to happen here? Whenever the apple collides with something, this function is going to be called, and whatever something we collided with is going to be passed through this parameter called collider. So through this parameter, we can have access to what collided with the apple and a lot of information of the collision, such as the normal. And let's just type collider here so we can have access to its members. And as you can see, we have the collider here, we have the game object that just collided with the apple, and we have this contacts variable. And this is the places where any sort of contact occurred. And this is also a vector. And anytime we have a collision, we know that we have at least one contact point, because if we collided with something, we might have one contact point. So if I access the index 0 of this, which I just proved that will always exist, I can have the normal here. And this is what we're looking for. So we basically want to reflect the direction along this normal. So I can just access the vector3.reflect method. And here it asks for a direction, something that's going to be reflected, which is of course our direction, and the normal. And the normal is just the normal of the contact point. But of course, this is going to return the reflected vector, so we need to reassign this to our direction. And this is pretty much it. So I'm just going to normalize the direction again, just to make sure that we always have a normalized vector. And this should do it. So let's go back to Unity. Let's try it out. There you go. That looks wonderful. Let's see if it works with our platform. It does not, because we don't have a collider in our platform. So if you just go to our Leaves Bush, component, physics 2D, add a box collider here. I'm just gonna expand our collider so we can see the gizmos. And you can see that it wraps up our geometry perfectly. And if I hit play, not our geometry, right, but our sprite, because we're not dealing with a 3D thing. and it just works beautifully. Okay, one more step of our game is done. Okay, even though the collision is working and the apple is actually reflecting when it gets to the wall, this isn't exactly looking right. Because as you can see, when I hit the bottom here, it should be game over because this is a not allowed movement. So what we need to do is to detect when the apple actually hits this place and don't allow it, right? So not the only way, but the best way we can do this is by checking which normal the apple is colliding against. So if we take a look here, I drew in red the normals that are not allowed. So when I hit one of those normals, it means that this is a game over. As you can see, there is a normal pointing up for this edge of the collider. That's the bottom part. And there are those 3 normals here for the platform. So what you can see here is that for the collider, only the normal 0, 1 causes a game over, and for the platform, only the normal 0, 1 is allowed. So we can use that onCollisionEnter2D function to check against which game object we are colliding with, and to check if that game object contains any of these components. Because if it contains the collider component, the collider creator component, it means that if the normal is this one, that's game over. But if we're colliding against the platform and it is anything other than this normal here, it also means a game over. So let's go back to Unity here, and we're going to be editing the Apple script. I don't know if I mentioned previously, but the onCollisionEnter2D only works if one of the 2 colliders has a rigid body attached to it. So for instance, in our case, the apple has a rigid body 2D, even though there's no gravity acting. It doesn't matter. It only needs to have this component attached to it. So both need to have a collider, of course, and at least one of the elements need to have a rigid body. So in case I occasionally disable this rigid body 2D, this function wouldn't get called because none of the 2 elements have a rigid body 2D. And inside this function, what I need to do is I need to try to grab a reference for either the collision creator or the platform, and I can check if they are null. What we need to do first, before we do any reflections, we need to try to get a reference for the collision creator and the platform. So I'm going to try to get a reference for the actually collider creator, I think. Here it is. So I'm going to call it collider creator with an lowercase c. And this is going to be equal to, we're going to grab a component from the object that's colliding with us, with the apple. So to do that, we need to go to collider, which has all the information with regards to the collision dot game object, and this is the game object that's colliding with the apple. And we want to check if this object has a component of type collider creator. We also need to do this with the platform. Collider.gameObject.get component angle brackets platform. There you go. So let's also hold a reference for the normal here, because we would need to grab this normal to verify a few things. So I'm gonna actually put the normal into a local variable, and as you can see here, a normal is a vector 2. So I'm gonna create a local variable of type vector 2, call it normal, and then I'm gonna say normal is equal to collider.contexts of index 0 dot normal. There you go. Now we have a reference for the normal and for the possible two other components that we may be colliding against. So if the collider creator is different than null, and what does that mean? If we try to get a component from this collider and it actually turns out to be something that's not null, which means that we grab something, it means that we are colliding against the collider creator or the game object that holds this collider creator component. So it must mean that we're colliding against the screen collider game object, right? And if we're colliding against the screen collider component, it means that the normal must be something other than the 0, 1 vector. So in case normal is equal to vector3, vector2 dot up, and that's basically short for writing 0, 1, this means we have a game over because we collided with a normal that we shouldn't. So in case the collider creator is null, it means that we aren't hitting the screen collider game object. So we're gonna try the platform. We are never gonna collide with the collider creator and the platform at the same time. So we're good to go with an else if statement here. So in this case, the normal must be something other than the vector2 dot up in order for us to have a game over. So if normal different than vector2 dot up, this means we have a game over. Another thing that I'm going to do here is I'm going to create a local bool that's going to hold a value for is game over. When I get into this function, is game over is false because we didn't check the collisions yet. But in case I get inside this if, it means that I'm colliding with something that I shouldn't be colliding with. In this case is the normal of the collider creator, which is that bottom part of our scenario. So in this case, is game over must be true. And we're going to use this local variable afterwards to check whether we should go to a game over screen or if we should change the direction of the movement. And this case is also game over because we're not colliding with that top part of our platform. And after we do these verifications for not allowed collisions, we can easily check for if is game over, and if it is, we're gonna do something like this is game over, okay? For now it's gonna be only a comment. But if it's not, we can just reflect the direction of the movement and keep playing. Okay, so there's not a good way for us to see if this is working or not, because if we have a game over, there's nothing we are doing so far. So in this case, we can just reload the same scene we're playing. As you can see here, in the assets folder, I have a scene called game. So in case I get a game over, I'm just going to reload the game scene. So basically I'm going to start over. And to do this, to load a level, to load a scene, you just go to the application class, and then you go to the load level function, and you pass in a string, which is the name of the level. In my case, my scene is named game, so I just type in game. So you're going to type in whatever the name of your scene is, or whatever scene you want to go to. In my case, I just want to start the same scene over and over again, so I'm going to pass in game. So whenever I hit something that I should not, I'm going to be loading this in again, okay? This is just a way for us to see if we're colliding with something that's not allowed or not. So just a way for feedbacking for now, but we're going to change this for a game over screen later. And if we go back to Unity and if I hit play, let's try the bottom of our scenario first. Boom, game over. Let's now try to get, this is going to be hard. I'm going to try to get the side part of my platform. Okay, so first of all, I need to increase the limits. So if I click on my leaves brush here, I'm going to press W to grab the movement tools. And if I try to move it to the limits of our scenario, we can see that the x value is now 5.2. So I must change the limit on x to 5.2. Just gonna reset the x value. I'm gonna play it again. Now I'm gonna try to grab this side part. There we go. I think I got it, and it was also game over, so this is working perfectly. Of course, the only way for feedback now is to reload the same scene again, but in future lectures we're gonna create a game over menu that's actually gonna tell us how good we did. So before we end this lecture, I'm gonna click on File and save my scene, just because, and I see you in the next video. Okay, so in this video we're going to implement the blocks that we actually need to destroy. If I just put a prefab here, if I go into my prefabs folder and if I drag one of these wood planks here, let's see if the apple hits one of these. I'm not sure where it's gonna, where the direction is gonna be pointing to. Okay, you see that the movement gets reflected, but the block doesn't get destroyed. So what we need to do here is inside the Apple script, we already have, of course, the function that detects collision. And since we have no special functionality for the block, we don't need to write a specific script just for it and to detect collisions and do pretty much the same thing we did here. Okay, so we can use the same onCollisionEnterToD function of the Apple to check if we're colliding against a block. Let's see the possibilities we have here. We can be colliding with the platform, and we can be colliding with the screen collider. These are the two possible collisions so far. Now we've added another one, which is the wood plank. So we have three possible collisions in our game. The apple can collide with itself, so this is not a possible case. Alright, so you can see that inside the onCollisionEnterToD function, we've checked two possible collisions. We've checked the collision with the collider creator, which is down here. We checked the collision with the platform, which is down here. So in case these two get missed, I must have been colliding with one of these wood blocks, so I don't even have to try to get a reference for it. I'm sure that if I don't get inside any of these two if statements, this one or this else if statement, if I put an else statement here, I must be colliding with one of the wood planks, because I just have, as said, three possible colliders I can collide with, and two of them already have been checked here. So the third one must be the one that remains, which is the wood plank. And what I want to do in this case is I want to destroy the element that I'm colliding with. Because I already have a reference for the normal, let's just make sure we pass in that normal reference we got instead of accessing the contacts again. So we can just pass in normal because we already have defined a reference for the normal here. So in this case, I just want to destroy collider.gameObject, which is the game object that took part in this collision. So you can use destroy. So you can use the destroy method for any kind of component. So if you want to destroy a specific component of an object, you can also use the destroy method. In this case, I'm using the destroy method to destroy the whole game object, so it's going to disappear from our scene. And if you go back to Unity, you can see that this is going to work flawlessly. If I try it, oh, there you go. Oh, it happened. As you can see, it got destroyed, the movement got reflected, there are no errors in the console, so it looks like it's working perfectly. What I also want to do is I want to increase a value that holds the number of blocks that I've already destroyed. And we're going to do this in another script that's going to keep our score. So inside the scripts folder, I'm going to create a new one, and I'm going to call it Game Manager. So any game has a game manager script that controls, let's say, the brain of our game, has some specific things to do with scores and all of that. In this case, we're going to keep our score inside this class. And for now, we can just keep it as a static integer. So public static int, let's say points. So what a static value is? A static value is a value that doesn't need a reference for an object to get accessed. So what it means in practical terms is that we can just access the class name, which is Game Manager, and then we already have a value for this attribute, which gets shared between all the instances of the Game Manager. So it's basically one value for all of the different instances that might exist, in case there's no instance that's required to access this attribute. So what I can do now inside the Apple script, instead of just destroying the game object, I want also to increase that value. So Game Manager, that's our class. Now we are accessing the class and not an object of that class. Dot points, and we can just increment that by doing plus plus. One thing that we must make sure we do. So once we start the same scene again, everything's gonna be resetted to its default value. Everything but static variables. So a static variable doesn't get its value resetted to its default. Let's say, for instance, that we have this points value that's currently 3, and I end up losing the game. So I'm gonna reload the scene game, and what I expected is that points gets back to 0, but it doesn't happen. Points keeps being 3 because this is a static field. So what we can do is we can define the void start here, which will be called upon initialization. So when the scene starts again, this function is going to get called, and what I can do here is I can force points to be 0. This is not necessary if points is not a static value, but in case it is, it's important that we do this to avoid having a wrong value, having wrong data inside this variable. And anytime you have static attributes, you must make sure you set them to default value inside the start function or the equivalent, okay? Also inside the Apple, we have this if that tells if the game's over. And instead of calling application.lowlevel game, we're going to create a static function inside the Game Manager. And the static term holds for functions as well. If it's static, it doesn't need a object reference to get accessed. So this is going to be void. It's not going to return anything. And I'm going to call it game over. So when the game's over, what's going to happen is I'm basically going to call application.lowlevel game, and that's it. So it's basically useless, but in the future, this function is going to change, and this is a good way for us to change the place where such important operation is happening. Now, instead of calling application.lowlevel game inside the Apple, we're just going to change this. We're just going to change the owner of that operation to be the game manager. So we're going to call game manager dot game over. So by doing this, we can make sure we do this kind of operations inside the game manager and not the Apple. So this is just a good practice of coding, okay? Yeah, so now we need a way to dynamically place these wood blocks inside our scene, and we're gonna do this in the next lecture. Alright, so now for the part where math comes in handy. This is the part where we'll try to instantiate the blocks in our game. Here I'm representing a system that will have 5 columns and 1 row. The problem with this is that if I initialize the blocks with the width that they have, they possibly won't fit in the entire screen. So if I put one more here, the last block is going to end up here, which of course exceeds the size of our screen. And if I just leave it as it is with 5 blocks, we won't reach the end of our screen, so this space is lacking content. And okay, this is what we have, and this is the ideal situation. As you can see, we still have 5 blocks, but we stretched each one of them so they can fit in the entire screen. And how do we do this? There's a little math behind this, and we're gonna explain this math in this lecture, okay? Alright, so what is important in this? So the variables that are important in this case are the screen width, and by important I mean what has to be considered in our equation. And I'll just explain why they're important. Screen width is important, block width is also important, and the number of columns is important. Actually, columns is a function of the screen width and the block width, because how do we get the number of columns? We get the number of columns, I'm gonna call it col, just by dividing the screen width, I'm gonna call it this SW for short, by the block width, I'm gonna call BW for short. So the columns is basically the screen width divided by the block width. But this of course can be a floating point value. So I'm going to get the floor of this value. So whatever value this is, let's say this might be 5.3, 5.4, 5.9. I'm always going to get the number, and I'm going to trash the decimal places. What the floor is that we always going to get the integer associated with this number. So 5 in this case, 5 in this case, and 5 in this case. The decimal places doesn't influentiate in the number we're going to get. So we're going to get the floor, and the floor is represented by this symbol. There's also the CO that does the opposite of this. But in this case, we're interested in the floor operation. So by doing this, we are making sure that the number of columns is always an integer, and I'm of course representing the columns by col. And just so we put it all here, this is BW, this is SW. Okay, so what I want here, I want a factor that when I multiply this factor by the block width, and I do this for each column, for each block, I get the screen width. It's a pretty basic equation, right? So if I do BW, which is block width, times the number of columns, which is already an integer, times this factor that I'm gonna call S sub f, scaling factor, I want this to be equal to SW, which is the screen width. So this scaling factor is equal to the screen width divided by the block width times the number of columns we have. So what do we do with this SF value? SF value is basically a value that has to multiply the block width. So the actual block width, the block width prime, let's say, and this is the target block width, has to be block width, the standard width of the block, times this SF, which changes for each configuration. So this SF is actually what drives the width of the block. Of course, we're gonna end up stretching maybe a lot our textures, but this is going to give us the effect of always filling all the screen, exactly as we did here. So in this case, BW times SF would be this. And since this block ends up here, we're going to start the second block later as well. So it's going to move even further. And if we do this 5 times, or the number of columns, we're going to end up having the last block ending at SW, which is here, and SW is of course the screen width. So this is our little golden equation, let's say, for having this nice behavior here. Of course, in the actual game, we will have a controllable number of rows. So you may have, another block here, another one here, and we can do this a lot of times. But the principle doesn't change because this operation is row independent, okay? It doesn't depend on the number of rows we have. So now that we know the mathematical principles behind this, well, we'll have some fun coding it. Now we'll do some fun stuff coding the system that will instantiate a lot of wood planks in our scenario, okay? So I can get rid of this one. I was using it just for explaining how we would destroy a single wood plank. And I'm going to create a new script, and this script is going to control the wood blocks creation, right? So I'm going to call it wood block creator. There you go. Open it up and want to develop. And hopefully you remember the mathematical approach that we did in the last lecture, because it's going to be useful in this lesson, as of course we will apply this principle in the code. It's not something that is too sophisticated, so it shouldn't be hard to remember. In this class, we will need a reference for all the wooden planks that we've created as prefabs in the first lecture of this series. So I'm going to define a vector of game objects, so an array of game objects, and I'm going to call it my blocks. I'm also going to get rid of the update function. I'm not going to be using it. What I want to is a function that gives me a lot of information with regards of the system that I'll be building. So I'll have two functions here. I'm going to have a function that's called create blocks group. This won't take any parameters. And I'm also going to have a function that's called get block information, or get blocks information. And I want this function to return me a lot of parameters that has to do with our system. I want to have access to the screen width. I want to have access to that multiplier that I'll need. I want to have access to the number of columns. And we have two ways of doing this. We have two ways of having a function that returns several values. We can have a structure that holds all the different values that this function will fill and therefore return. Or we can pass them as reference parameters. A reference parameter is a variable that's passed in to the function, but as a reference. So anytime you modify this variable inside the function, it will modify the actual variable that was passed in as parameter. So this function will have a value reference to the block width, because this is something that we already have access to. This function will have a reference parameter, that's the screen width, because we don't need the screen width in pixels. We need the screen width in world coordinates, because our block width is in world coordinates. Okay. We'll also need the number of columns, and that's actually an integer. And we'll need that multiplier, that scale multiplier. And that's pretty much all we need. So as said, we'll need the screen width in world coordinates. And how do we do to get the screen width in world coordinates? First of all, we need a reference to the camera. I taught you earlier how to get that reference to the camera by exposing a variable of type camera here and manually assign it in inspector. But in this lecture, we're going to do something different. We can have access to the camera that's actually rendering our game by a static variable that's inside the camera component. So I'm going to have a reference here, a local reference. I'm calling it cam. And this is going to be camera.main. As you can see, the first enabled camera tagged main camera. And if you go back to Unity, there's just one camera here, this one main camera, and it has a tag main camera. So every time I get access to that main attribute, Unity will search for the first camera it encounters that has this tag main camera. In our case, there's just one, so we can be sure that this one will be returned. Alright, so now how do we fill the screen width? So the screen width will be cam.screen to world point, and we want to pass in the rightmost part of our screen. So a new vector 3. And for x, of course, we need to have screen.width. That's the width of our screen. For y, it doesn't really matter. So 0, 0 here. I'm going to show you what does this imply in a few seconds. So I need to subtract the leftmost part of our screen. So I need to subtract a point. cam.screen to world point, new vector 3, and this one is 0, 0, 0. But this returns me a vector. If I subtract these 2 points, it gives me a vector. So I'm just gonna wrap this subtraction in between parentheses, and I'm just gonna type in dot x because I want to get the x component of this vector, and this is actually gonna tell me the screen width. What's actually going on here is that when I type screen.width 0, 0 and I try to convert that into world coordinates, it's going to get this point of the screen and convert that into world coordinates. And when I get 0, 0, it's going to get this point and convert into world coordinates. So what I'm doing is I'm subtracting these 2 points. So I'm going to get a vector that goes this way, but this is of course in world coordinates. And as you can see, the y and the z components of these vectors are 0, and I'm grabbing just the x component, which is going to give me therefore the screen width in world coordinates. And as said, the columns is basically the screen width divided by the block width, but we want the integer of that number. So columns is going to be screen width divided by block width, and we could just do a typecast of this entire thing to an integer. It's gonna wrap the division into parentheses, and I'm going to typecast that to an integer. And typecasting to an integer is the same as doing a floor operation, because it's going to get rid of that floating point bit. And for the scale multiplier, what is our equation? We basically want the block width times this scale multiplier times the number of columns to be equal to the screen width. So our scale multiplier will be screen width divided by block width times the number of columns. Alright, so scale multiplier, I'm just gonna copy from that. Screen width divided by block width times the number of columns. There we go. So all the information we need is going to be filled up by this function. So in this create blocks group function, I'll have to have those local variables that will hold the value for screen width, columns, and scale multiplier. So I'm going to define 2 floating point values, screen width and scale multiplier. I don't need to give them a value because they're going to be filled up by this get blocks information function. And I also have to have a variable for the columns. And what I do now is I can call the get blocks information function. And what do I pass in for the block width? I know that all these blocks inside this array, they have the same width. And I'm talking about world coordinates width. So let me give you an example here. I'm talking about the distance from this point, which is the leftmost point, to this point, which is the rightmost point, in world coordinates. How do I have access to that? You can see that each sprite has a sprite renderer, and inside this component we have this information. So to access that, I'm going to assign this to a local variable, float block width, and I can pick any of the indices of these blocks, given that it's an index that exists. So I'm going to get 0 because I'll assume that there's at least one block that's filling this array. Dot get component, and I'm going to get the sprite renderer component because I said the information of the size of this block is inside this component, and I can access bounds from here. So this is actually a cube, or maybe a box that will wrap this sprite. It's something that's not visible, but it exists. And we want to access the size, so the total size of the box. The box is of course a non-visible box that encapsulates our sprite in the world. And we want to have access to the X component because this is our width. And here I can pass in the width, the block width. I can pass in the screen width as being an out parameter, so out screen width, out columns, and out scale multiplier. So now we're getting all the information we need to build that structure. Actually, I'm forgetting something here. I also need the screen height, and you'll see why within a second. So I'm just going to define the screen height, and I'll have to have the screen height as being passed in as an out parameter here as well. So out float screen height, and I have, of course, to fill it up. So now you already know how to do this. This is screen height, and I'm gonna encapsulate all of these into parentheses, so I'm gonna already insert one. So cam.screen to row point, and I'm gonna get the upmost bit of our screen into world coordinates. So this is going to be 0 for X, or anything you want for X, it doesn't really matter. Screen.height, which is the upmost part, and 0 for Z, minus cam.screen to world point, new vector 3, and 0, 0, 0 again. But this time, instead of X, we're gonna grab the Y component. And we need to do this because we'll have to place the elements here. So the center of our game is of course here. But if we subtract half of the width and we sum half of the height, we end up being here, so we are ready to put the element. But there's one problem as well. Our element has center here. So we need kind of to sum half of the width of the block and subtract half of the height of the block to get it positioned here. Instead, it will be here. So wouldn't it be easier if we just put the pivot of this 2D element as being its top left corner? And yeah, this is a good approach. We can just go to Unity, select all of these 3 elements. Actually, they're sprites. So select all of their 3 sprites and change the pivot here as being top left. Just hit apply. And now all the position is given by its top left corner. But you see that the collider has been dislocated. So we can just reset its collider to get it centered correctly. And we can select all of the sprites here in our prefabs folder. And in the little gear here, we can reset the information for the box collider. So now we can see that collider is perfectly centered for all of the 3 variations. And since this is a rather long programming session, I'm going to be ending this video here just after I get rid of this error here. It said no overload for method get blocks information takes 4 arguments, and that's because we added one more argument to our function, but we didn't add this parameter into the place where we actually call in this function. So as you can see, just after screen width, we placed another parameter, which is the screen height. So we need to define this screen height here as being a float. And we need to pass in out screen height. Oops, I've already defined it here. Sorry. There we go. Now it looks good. We won't have any errors, but this won't have any functionality. We of course need to instantiate these blocks, and we're going to do this in the next lecture. Okay, it was kind of lame to have to end the last video in its middle, let's say, but we have this restriction that we can go over 20 minutes. So we're back here, and in this last bit, we're going to actually instantiate the blocks. Of course, we will need a two-dimensional array because we're dealing with both columns and rows. And I'm also going to define a variable here that's going to be the number of rows that I want to have for this block of wooden planks. So rows. And my two-dimensional loop will go as follows. For int x starts out as 0 and goes up to the number of rows. At each iteration it's summed up by 1. And we'll do the same for y. Instead, it goes up to the number of columns, and at each iteration we're going to sum it by 1. And for each of these items that we're placing, we have to pick randomly one of these blocks. So to do that, we just have to grab a random index, and we already know how to grab a random integer. So we can just apply this knowledge to grabbing a random game object out of this set of blocks. So first of all, let's get a random index. So int random index. This will be equals to random.range between 0 and blocks.length. Since the last integer is excluded, we can just pass blocks length. We don't have to do blocks length -1, afraid that we may end up grabbing an index that doesn't exist. Because if the length of this array is 3, we're going to randomize a value between 0 and 2, so 0, 1, or 2. So we can make sure that we're not going to grab an index that doesn't exist. And the actual game object, the random geo, is blocks of index random index. There we go. So now we have to instantiate a copy of this item. We can just place it in the world because it doesn't exist in the world. It only exists in our prefetch folder. So to instantiate it, I'm going to assign it to a local variable. Instantiate it, if I can type, instantiated geo will be instantiate random geo. And this function returns an object, and I'm trying to assign it to a game object, so I need to typecast it to a game object. Alright, so this is good. Why I didn't assign any position in the instantiate function? Because I surely can assign positions. Because I already have a reference to the instantiated geo, so I can deal with its position, scale, and all of that, just so we don't get a line that is too long. So first of all, we need to assign its position. Instantiated geo dot transform, which is its transform component, dot position. We're gonna assign no position for it. And now let's see how we are actually computing this position. We know that actually we want to grab this top left corner here. And this top left corner has x coordinate minus screen divided by 2 and has y coordinate screen height divided by 2. But I have a loop, so I have to keep in mind that I need to displace this initial position depending on my current elements of the loop. So on the x-axis, I want to displace the block width times my current column, which is y, times the scale multiplier. So make sure we are displacing them at the right rate so that the end block ends up just at the rightmost part of our window, of our game window, okay? For the screen height, we actually need to subtract whatever our block height is, so we will need that information as well, times x times, and that's it. We don't have a scale multiplier for the y component. So let's put that into Unity. So we need to give this man a new vector 3 position. The x, as said, will be minus screen width divided by 2 plus, and here comes a big bunch, block width times the scale multiplier, and don't forget times y, because we need to take account for the current column we're actually computing. For the y, this is a nice trick. You can put a comma here, hit enter, and continue in the next line so you don't get something that goes too long in here. Alright, for the y, it's going to be screen height divided by 2 minus block height, which we don't have. So we need to define this block height. And the block height will be pretty much the same as this guy here. Just Ctrl C, Ctrl V here. Just copy and paste. And instead of grabbing the x component of the size, we're going to be grabbing the y component. Of course, we could easily store this into a variable. We store the sprite renderer of the index 0 into a variable and then access its bounds and then its size and making it look better. But it doesn't really matter because we'll only be calling this once in the start function, so that's not a problem. And we need to multiply this by x. And in the z parameter, I'm going to pass in 0 because this is two-dimensional. And we're not done yet. We need to take into consideration that we are possibly changing the scale of this element. And this is given by this scale multiplier. So we need to change the scale of this element. So the instantiated geo.transform.localScale will also receive a new vector 3. And for x, we want to change its width. So it's going to be whatever the value it is right now, instantiated geo.transform.localScale, and this long.x, so whatever value it is right now, but times the scale multiplier, because as said, we need to change its scale so it fills our entire screen. And in the y and z axis, it's going to remain whatever it is. So instantiated geo.transform.localScale.y, and in the z we just have to pass in 1 because it doesn't really matter, right? And I guess this is it. So let's just make sure you call this function inside the start function. So we are creating our blocks, create blocks group, and hopefully this will work just okay in Unity. So let's go back to Unity. Let's check for errors. There's none. So I'm gonna get rid of this wood plank 1, delete it, and let's actually create a new game object just so it contains this woodblock creator script. So game object create empty. I'm going to assign this woodblock creator script because it has values that needs to be filled in the inspector, so blocks and rows. And for blocks, I'm going to assign each of my prefabs, so wood plank 1, wood plank 2, wood plank 3. So now that these guys are there, I just need to assign a number of rows. So let's start by putting three rows here. Hit enter or hit play, and it works. It's just great, right? It's just mathematics. So as you can see, we have that they are perfectly aligned with our view. And man, I didn't expect this to work right away, but it did. So let's try to play our game. And it looks like we get a very nice working game right to this point. Of course, there's one thing we need to start working on, which is making it better looking. We have nice sprites, but we don't have any sorts of particles, we don't have sound, we don't have animations. So we need to start working on that. And also, if I change my aspect ratio here, this is ugly, I know, but just to explain something, of course, my wood planks, they're totally dynamic, so they're gonna fill my entire screen, but my platform can go any further. So this is something we need to correct. Okay, this is a problem, and we need to do this to allow that our game is playable in any sorts of screen resolutions. Alright, so this is going to be done in the next video, and this is it for this one. Alright, so for this video we're gonna set up the limits of our platform dynamically. Just before I do that, I'm gonna set up the aspect ratio to be something else because that was looking ugly. And this is pretty simple actually, based on a lot of stuff we've already studied. So we just need to get the rightmost bit of our screen, which is going to be this point. But if we center our platform on this position, we'll end up having that it's off screen by half of its size. So what we can do is just center it by this position minus half of its x size, right? Because if this is its full x size, half of its x size is going to give me this position. The same is going to apply for this side, and I'm going to be able to move freely and dynamically. In case I change the screen resolution, this is going to be applied flawlessly. Okay, so I'm going to go back into Unity here, and for that I'm going to have to open my platform script. This limit on x can be changed to a private value because we won't need it anymore to be public because it's going to be dynamically set. And I'm also going to rename it refactoring and change its name to limit on x. So everything that has this reference gets its name changed to underscore limit on x. And in the start function, I can set this limit dynamically. As we already know, you can get a reference to the camera by doing camera.main. I called mine cam. And now we need to get the width of this sprite, the sprite of the platform. And so I'm going to add this to a floating point value. So platform width, this is going to be equal to get component. I'm going to get the sprite renderer component because we already know this is where the bounds are located. So dot bounds dot size dot x divided by 2. Or instead you can get the extents, which is half the size, so you don't have to divide it by 2. Pretty much the same thing, but the only difference is that the extents is always half of the size. Now what we will do is we'll grab the rightmost point of the screen into world coordinates. So cam dot screen to world point, and the rightmost point will have its position on x being screen.width, y doesn't really matter, z neither, and we have to subtract the platform width from that. Of course, the only thing we need to do now is to apply this back to the limit on x. There we go. This looks pretty good. This looks exactly what we need. So once we go back to Unity and we hit play, oops, there is an error here. Of course, I'm grabbing the point in the world space, but I actually just need the x component of that point. So dot x. Otherwise, I would be subtracting a vector 3 from a float, and this is not allowed operation. So I need to be float. The x component is a floating point. The platform width is a floating point. So now we have an allowed operation, and this is good to go. So if we go back to Unity, this guy should be all set. And if I hit play, let's try to move our platform, and it's just perfect. Okay, so in case I change my aspect ratio, let's do something more extreme. Let's go for this one. And we can move to the borders of our screen. That looks just Beautiful. So we can play our game a little bit. It's working, it's just fine. Of course, as said, there are some animations lacking. We need to put sound on this. We need to put particles to make it shine, to make it beautiful. And we're going to do this from the next lecture on. Okay, so in the next lecture, we're going to start setting up our particles. There will be particles when we hit the platform. There will be particles when we destroy a block. It's going to be amazing. But for this lecture, this is it. And I'll wait you in the next one. So now it's time for us to start giving this project a little bit more of life, and we're gonna do that using particles, sounds, and animations. Not in this particular order, but we're gonna start with the particles in this lecture. So first of all, we need to create the particles that we're gonna be using, and you probably still have a little bit of memory about those particles that you've seen in the demo that was presented in the first lecture. So you can probably remember what it was all about, and we will need two particles. We'll need one particle for when the apple hits our leaves bush, and we will need another particle for when the apple hits the blocks, which you can only see when you hit play. So let's start by creating the particles that will be released when we hit the leaves bush. So the sprite that we'll be using for that is in game, and it's called the leaf particles. And to create a particle system that will actually instantiate a lot of these particles at the same time, or with a space timing, we need to create a particle system. So go on game object and particle system. There's no such thing as a particle system 2D, but a particle system works just great in 2D and 3D. You just need to set up a few things depending on the behavior you're trying to achieve. In our case, we don't have to set up much for it to work in 2D because it sort of already works fine. Let's just see where it is. You can see that if I zoom in too close, it doesn't appear. So if I zoom out, it shows. So we know that if I disable the 2D option here, you can see that this is a layered scenario. And if I bring this a little bit further on the Z coordinate, you can see that it starts showing because it's now rendered on top of the other stuff. So in case it doesn't show, it might be on the back of all these other layers. So just make sure that you put it on the front, which is negative. This is curious, but so just need to make sure that this is rendering. So I'm gonna set up mine with a -1 position on the Z-axis. Now we can go back to 2D, and there we go. You can see our particles. And if you go down here, there's an option called renderer, and this is where we actually control what are you actually instantiating. So as you can see, there are a lot of these white halos being instantiated at every frame, or a lot of them being instantiated per second. So we need to change this for our leaf particles sprite. So first of all, we need to create a material to hold this information. So I'm going to create a new folder inside my assets folder. I'm going to call it materials. Inside it, I'm going to right click, create material, and I'm going to call it leaves particle. Alright, so to make this a particle, we need to change its shader. So shader is basically how the object gets rendered in the game. So we need to click on the actual shader that we're using. In this case is the standard one, and there's a particular subset called particles. And in this one you have a lot of particles, a lot of shaders, a lot of behaviors in terms of how it displays on screen. And for this case, we're going to be using alpha blended. This works great for us because the other ones, they kind of add themselves in terms of color, and the alpha blended stays just the same. I'm going to give you an example. So I'm going to choose additive for now, just so you can see how it works. And I'm going to select a texture for it, which is of course our leaf particles. And now I need to say that this particle system is going to use this material as its default particle. So I'm just going to go on rendering here, and for the material I just need to drag my leaves particle here. And you can see that it kind of adds to the background color, and this is a weird behavior. And the one that's going to work great in this case is the alpha blended one. Alright, so this doesn't add, this just renders the particle as they are, okay? You can also change the tint color. This is going to multiply the color of the particle itself. So this is not required because we can also add a color to each particular leaf. So by clicking on the particle system here, we have a lot of parameters, and I mean it, a lot of parameters that we can control. Let's start by changing the orientation of these particles. So I'm going to go over on start rotation, and I'm going to increase it to maybe 90 degrees or something close. And we can actually randomize between two different constants. So just click on this little down arrow here and choose random between two constants. And now we can pass in two different constants that we'll randomize between. So maybe 0 and 180. This looks nice, but they aren't falling. So we need to add a gravity modifier. Let's try 1. And as you can see, they are now falling. So the bigger the gravity modifier is, the harder they will fall. So for example, 10, you can barely see them, right? And maybe 0.3, they go even higher because it means that the gravity modifier isn't that big. If you want to have a gravity that works the other way, you can just add a negative number here. So it works as if there's some kind of attraction field on top of the screen here. But in our case, I'm going to try to use maybe 0.7, I guess. And you really have to play around with those parameters because you can do a lot of stuff that's actually really cool. And I'm also going to change the size. So on start size, I'm going to bring this down a little bit. And the speed, I'm going to make it to get a random value between two constants, so I can get a nice variation for the speed. So maybe between 7 and 8 or something. Actually, oops, I'm sorry, I ended up randomizing the lifetime, but I mean the speed. So I'm going to go random between two constants on the speed, between 7 and 8 perhaps. It looks too much. Maybe between 3 and 5, that's too low. 5 and 6. So let's play around with these. We can also change the start color, so this color will also multiply the color of each particle. And this can also be used as a random parameter. So just click on this down arrow, random between two constants, and now we can change perhaps a white color and one that is sort of a reddish color, because it will give this effect of a burnt leaf, which is very cool. And we have this effect on the leaves brush as well, so it kind of adds to the realism, right? Or graphical fidelity. And one other nice thing we can do is we can try to increase the amount of particles that are rendered at each second. So just expand emission here, and you can increase the rate. So the bigger the rate is, the more particles per second will going to be emitted. And I didn't change much here, so I'm going to try 40. That looks like a lot. Maybe 20 looks good. And I'm going to change the lifetime so they die earlier. Maybe 2, 1.2, 1.3, 1.4. That looks good. But there's a problem here. You can see that they disappear out of nowhere. They're there, they're looking good, and they and then they disappear. It would be nice if we have some kind of fade based on their lifetime. So the closer they're getting to their death, we want to fade that. Okay, so we can do that pretty easily. You can just enable here color over lifetime, and then there's a nice curve for you to edit. Actually, a gradient editor. So we'll start out in this point. So this is the starting point, and this is the end point. And for the end point, we have this point up here, and that means the alpha. And the down point here means the color. So for the alpha, I want to bring it down to 0 because I want to fade that away. But I don't want to fade it linearly. I want to have the alpha full set until maybe this point. So I just click here to add a new alpha point, and I can just, you know, drag it down if I don't want it anymore, so it's going to delete it. In my case, I'm going to click it here. I'm going to put the alpha back to, you know, 255, which is 1. And you can see that they start to fade out when they're getting close to their death. So this looks very, very good. And something that's not cool in this is that they're looping. So we're going to disable this looping option, and we're going to press stop and then simulate. So this is actually going to be the simulate we get in real time. But you can see that this is emitting for too long. So we can just change the duration for maybe, you know, 0.5. Oops. And that means that we're going to emit particles during 0.5 seconds, and then we're going to stop. Alright, so this is where it gets tricky. This is where we need actually to control the parameters. So I can see that the emission is too low. So I'm going to increase it by, you know, maybe twice as big. Still doesn't look good. Maybe 100. And this is starting to look nicer. But I want to randomize the speed more as well, because it looks like they are going the same speed. So I'm gonna make this even bigger. Maybe a start speed varying between 7 and 3. Now this is starting to look like a mess, and this is the behavior I want. Maybe not too big, maybe just 6 as the maximum. Alright, and this looks good. We can also add rotation over lifetime, so we can just add this option, rotation over lifetime, expanded. So it means that we're gonna have 45 degrees of angular velocity for each particle. This can of course be randomized. Let's see what we get here. Oh, this is nice. I'm just gonna randomize between minus 45 and 45, so some particles are going to go in the other way. And this looks pretty good. Okay, so this looks good enough, and I'm gonna make a prefab out of this. I'm just gonna change its name. So up here, I'm gonna click on particle system, and I'm gonna change it to leaves bush. Actually, leaves particle. And on the prefabs folder, I'm just gonna drag this, and there you go. We have a prefab. Let's see if it's working. There you go, it's working. Very nice. Gonna delete these, apply the prefab changes just in case. There you go. So I'm gonna save my scene, save my project, and I'll see you in the next video so we can set up the particles for the block destruction. So in the last lecture we created the leaves particle. If I instantiate it here they are, pretty nice. Now we need to do the blocks particle, and I'm gonna create a block just so we have sort of a feeling for the size. So under prefabs, I'm gonna create one of these wood planks, put it in scene, double click to focus on it, and I'm gonna create again a particle system. So game object, particle system. I'm gonna change the Z axis to -1 so we can see it. And first of all, we need to create a material for the other particle. And what the other particle is, you can see on sprites game, we have this wood particles here, and this is actually the wood destruction particle. It doesn't look like, but it is just a white square, and we're gonna customize it to make it look like it is a little pieces of wood that are coming down from this wood plank here. So I'm gonna create a material based on this wood particle. Gonna call it, I don't know, wood particle. Change the shader for particles, alpha blended, and choose a texture here, which will be of course this wood particles here. And I'm gonna change this particle system's material to be the wood particle we just created. There you go, so it's working. Okay, so first of all we need to correct this gravity modifier. So I'm gonna put it to be I don't know, maybe 1. Bring down the size to 0.3. I don't know, 0.3 looks good. And now I'm gonna introduce you a new parameter. You can see that they are spreading too much. So I'm gonna go on shape here, and here I can edit the actual shape. In the scene view I can see what the shape looks like, and it's a cone. So I want to change it to a box. Just click on shape here, change it to a box. There you go, so it doesn't spread that much, which is something that I particularly don't like. And now I'm gonna expand this box shape by clicking on any of the corners here. Gonna expand on X, contract on Y, bring the emission up, you know, for maybe 100, and pull this down a little bit. Oops, this is actually the center. So I think the gravity modifier can be increased a little. No, this is too much. Let's see what we can do so we can get rid of this effect here. Maybe we can set the gravity modifier to be positive and the velocity to be negative. Yes, this looks good. So we're gonna randomize between two negative values. Maybe -2 and 0. And the color, what I'll do for the color is I'm just gonna bring this down a little bit so I can see the colors of my wood plank, and I'm gonna choose random between two constants. And for the first color, I'm gonna get the darkest color of this wood plank particle. And to do this, I can just grab this color picker here, and I can choose any color anywhere on Unity. And I'm gonna choose the darkest one here. Just click on it. There you go. And for the second one, guess what? We're gonna choose the lighter. So maybe this one up here looks good. And there we go. So now we have a randomized color that kind of reminds us of the colors of this wooden plank, and this is a nice effect. Something else I want to do is I want to decrease the lifetime here. I'm gonna put maybe I want them to die before they reach this bottom of the screen here. So maybe 0.7, I guess. Yes, 0.7 looks good. I'm gonna randomize the scale as well. So random the scale between two constants, maybe 0.1 and 0.2. And we can also make the scale go down depending on time. So we can go here to this size over lifetime transform, and this is a curve. So what this curve tells us is basically what's the size depending on the lifetime. So on the left part of this graph is the size just when the particle starts its life, right? So if I bring this down, you can see that the size just when it gets initialized is pretty small, right? But we want the opposite. We want it to be really small. Actually, we want it to be 0 when the particle ends its life. So I'm gonna grab this right point, I'm gonna pull it down. There we go. So we can add one more point here so it doesn't get so linear. Now this looks nice. So now where the actually configuration comes in, because we need to, now we're gonna check if this is working nicely, because we're gonna disable the looping. So press stop, simulate, and of course the duration is just too big. So I'm gonna decrease the duration to maybe a second. I think that's too much, maybe half a second. Not enough particles, so I'm gonna go down here. Maybe I can increase the size as well, so 0.3. And when I hit play, yes, this is looking better, but I could use some bigger rate here as well. So 130. I think this start color is just too dark, so I'm gonna pull it up a little bit, try again, and it actually looks better. So this is all about, you know, trying things out and trying different patterns, because it takes a few minutes to get something that looks good, and this looks good for me. So I'm gonna change this to wood particles. Go under my prefabs folder, I'm gonna drag it here, and this guy is now created. I'm just gonna rename it to wood particle because we have a pattern here. This is leaves particle, and this should be wood particle, just because it's beautiful. Okay, let's see if it's working. Gonna drag it here. It works. So I'm gonna select my particle here, gonna hit apply just in case as well. I'm gonna delete this, save my scene, save my project, and now it's time to actually instantiate those particles when it's time. And we're gonna do this in the next lecture. Actually, just before I end this lecture, I'm gonna delete this wood plank that we've used just for reference. I don't need it anymore. I'm gonna save the scene as well, and I see you in the next lecture. Okay, so now it's time to put these guys in real time in our game. Let's start out by checking where we should actually get references for these. So we need to instantiate them when the apple hits something. So of course we need the references for these guys in the apple script. So I'm gonna open up the apple script here, and I'm gonna have references for two game objects. So public game object. One is the wood particle, and the other is the leaves particle. Okay, so for the wood particle, where do we actually need to instantiate the wood particle? We need to instantiate the wood particle whenever we hit one of the wood particles, and this is actually inside this else statement. As you can see, we are destroying one of the wood planks, so we can easily instantiate one of these particles at the position of one of these wood planks, and we'll get the fact we're looking for. So I'm gonna instantiate, and I want to instantiate the wood particles where? At collider.gameObject.transform.position. And what is the rotation? I want to rotate it. I want the zero rotation for this guy. So I just pass in quaternion dot identity. So the identity rotation is just, it means no rotation, right? So this is just a static variable that holds this value. And note that I'm instantiating this guy before I destroy the collider, because if I try to instantiate it after I destroy the collider, I can't do it, right? Because I would lose a reference for this game object here. So make sure you're instantiating the particle first, and then you're destroying the collider. So when I go back to Unity here, and inside the Apple script, I need to attach these two guys here, and on the prefabs folder there's the leaves particle. I'm gonna put it here. And there's the wood particle. I'm gonna put it here. And if I hit play, let's see if it works. It looks like it does, but there's a problem. As you can see, the position of these wood planks, it's always top left, but we want to get the particles on the center of these wood planks. So we actually have to sum half of the X size and we have to subtract half of the Y size, right? So we need to get the sprite renderer component of the wooden plank we're trying to destroy to get its size, and then sum this up to the particle's position. So right here in MonoDevelop, first of all, I'm gonna have these references to the sprite renderer. So I'm gonna call it renderer, and this is going to be collider.gameObject, which in this case would be the wood plank dot get component. So we're getting a component from that wood plank, and the component is sprite renderer. There we go. Okay, so I'm just gonna put this position inside a local variable so we don't have to access over and over again. As you can see, it's pretty big to write this, so I'm gonna put it inside a variable. So wooden plank position is going to be equal to collider.gameObject.transform.position. Phew, and this is all that goes inside this local variable. It's just for shortening, right? So instead of writing all of this, we're gonna write just this not too little but not too big name. So now we want to define the particle instantiation point, which will be a new vector. And as you can see, we have to grab the X component of the position, but we need to sum it up to half of the size of this sprite. So wooden plank position.x plus renderer.bounds.extends, which is half the size, .x. And we need to do pretty much the same thing with y, but instead of summing up half of the size in y, we need to subtract it, because the y component is positive if we go upwards, but we're going downwards. And for z, let's pass -1 just to make sure that we will see the particle on the screen. So instead of passing this position here, I'm going to pass the particle instantiation point, which I've just defined. Let's see if it works. And it looks like it does. But as you can see, we're ending up with a lot of these wood particles on screen, and I would like to get rid of them as soon as they're not appearing anymore. And think with me here, how long does it take for the last particle that appears to disappear? It takes the duration, the time that the last particle will take to render, this is the duration, plus its lifetime. So maybe there's a particle, this little brown guy. Let's say that this is the last one. In the worst case scenario, it took half of a second for this to appear. And it's going to take, in the worst case scenario, 0.7 seconds for it to disappear, because it's its lifetime. So we have to destroy this particle 0.5 seconds plus 0.7 seconds after it got instantiated. And we can do this pretty easily. Inside this Apple script, we can just access the destroy method, and we want to destroy the particle we just instantiated. So first of all, we need to grab a reference for these. Or particle. And this is going to be whatever this function gives us, but remember that instantiate gives us an object, and we need to typecast this to a game object. And now we can safely destroy our particle here, and if we hit comma and a space, you can see that it asks for a float t, and this is an override of this method destroy. You can destroy anything t seconds after you call this method. So here we can just pass 1.2f, and this is the time, the worst case scenario it's going to take for all the particles to disappear. Actually, the best way to do this is to grab the actual variables and not putting a static value here. Because it might happen that you go here and you change the duration and you forget to change this static value here, and you'll end up having a weird behavior and you don't know why. Maybe you don't remember why. So the best thing you can do actually is to get this component, which is a particle system, and get the duration, which is a variable of that, and get the start lifetime, which is also a variable. So what you can do here is to grab this component. So we're going to assign this into a local variable of type particle system. I'm going to call it particle system with a non-capitalized p. And this is going to be equal to our particle, which is the game object that actually contains this component, dot get component, and the component we're looking for is particle system. And here, instead of passing in this static value 1.2, we're going to pass particle system dot start lifetime, oops, plus particle system dot duration. And as you can see, these variables, they're actually not read-only. You can write to them, so you can edit your particles in real time. And now if you go back to Unity, oops, there's a particle in my scene. I'm going to remove this wood particle here. Right click, delete, hit play, and once I hit one of these wooden planks, okay, there's a particle here. Let's just double click on it to focus, and let's keep this item selected, see if it's going to disappear after all the particles disappear as well. And as you can see, it does, because I had this particle selected and now it's gone. So it's working. Okay, so one particle is done. Now we need to place the leaves particle, and if you notice, the leaves particle will never appear twice in the scene. There are cases that the wooden plank will appear twice, in case if we hit two wooden blocks at the same time. Let's see if we can do this. There you go, we hit twice. So we got two particles at the same time. But for the leaves particle, we'll never have two at the same time, because it takes time for the apple to come down and hit the leaves bush again. So we can just keep one leaf particle in the scene and just play it, simulate it, whenever we hit this leaves bush here. Okay, so if you pay attention, if I just leave this one in my scene, when I hit play, it plays, and I don't want that. This is because we have this play on awake option selected. So if you deselect that, and if you hit play, it doesn't play automatically again. It's going to wait for my signal to play. I'm just going to apply these changes to my prefab. So instead of instantiating a particle anytime we have a collision, and instantiating something is an operation that takes a lot of computation, we're going to keep this one in our scene. We're going to keep a reference to this one, which is on Apple, and instead of passing the prefab leaves particle, we're going to pass in this instance of our prefab, which is in our scene. And we're going just to change its position and play it. Very simple. So here in MonoDevelop, let's see where we actually hit a platform, and here it is. So when I hit a platform, I'm going to change the position of this leaves particle element. So leaves particle dot transform dot position, I want it to be the platform position. So platform dot transform dot position. We have a reference for the platform right here. Okay, so now we have to play the particle, because as you saw, it will just stand by until it receives a command to play the particle. But to play the particle, we have a reference to a game object, and we have to have access to the component called particle system. So what we can do is just to access the component called particle system that's inside this game object. So lives particle dot get component. The component is called particle system. How do I know all the names of this component? You just get used to it. If you're coding, if you're practicing, you'll get used to the name of the components, and at some time you don't even need to look at the documentation. You will have all of them in your head. It's just a matter of practicing. So I access this component dot, and there is a method called play. It makes perfect sense, right? So I'm gonna invoke this method play, and since it's not looping, I'm just gonna play it once, and it's gonna wait again. So if I come back to Unity here and I hit play, let's try this out. There we go, and this looks nice. This looks nice. As you can see, there's a little gizmo of our particle in the game view, and you can see that it stands by in the last location until it receives a command to play again. Alright, so this part is done. We have particles in our game. It's time to move up, maybe creating some menus, maybe creating some sounds. You'll see in the next lecture. Alright, so in this video we're gonna create an animation for our platform, because when the apple hits it, we want to, I don't know, turn that into something more dynamic. We want to create an animation. It's basically going to be the platform popping when the apple hits it. And okay, to create this animation, we're gonna use the built-in animation system in Unity, where you can actually animate properties. So if you click on a platform here, all of these properties you have here, I don't know, position, rotation, scale, the fields from the sprite renderer, you can animate that through the animation system. And we're gonna use that, and they're basically gonna animate the scale. So let's say that the scale is gonna do something like that when the apple hits it. So just a little bit of popping. And to actually create this, we're gonna use the Mechanim state machine based animation system that Unity has since version 5.0, I guess. And I'm gonna quickly remove this because this is from when I was playing with Mechanim to see if everything was gonna go well. Okay, so to start off, we're gonna bring the animation tab, and this is where you actually can create the animations you want. So go to Window, Animation. And to avoid this floating tab here, because whenever I click somewhere else, this tab is going to disappear, I'm going to put it right to the side of the game tab. So Window, Animation. Now I'm going to click on the animation here, and I'm going to drag it right by the side of this game window. There we go. Now we can see the animation and the scene view. I'm going to pull it to the left a little bit. Alright. So I'm going to select the item that I want to animate. And it says here, it's kind of hard to read. Let's see if I can see it better. I'm gonna hit Shift Space to maximize this view. And it doesn't work with the animation view, it seems. Oh god. I'm gonna expand this just so we can read what's actually written here. Okay, so it says, to begin animating LiveSbush, which is our object, create an animator and an animation clip. So basically we need to create an animator, which is basically what drives the animations for the game object, and this uses Mechanim, and the animation clip is properly to actually animate something. So if I hit create, this automatically is going to attach an animator to my LiveSbush, and it's going to create a new animation clip for us. So before I do that, I'm just going to quickly go into the assets folder, right click, create, and I'm going to create an animation folder, animations. Actually, I think I'm going to just do one, but animations should be good. So now go to animations, window animation, select the leaves brush. This is what I'm talking about. You know, when you have this floating tab and when you click somewhere else in the hierarchy or in Unity, it just disappears, right? So just click on the leaves brush and then go to the animation tab, hit create, and it's gonna basically ask you to save this animation clip. I'm gonna go inside the animations folder and I'm gonna save this as popping. So the popping animation basically is gonna animate the scale. There's two ways you can do this. You can just drive the properties through the inspector here, but I'm going to specifically say that I want to animate the scale and just the scale. Be very careful with this, because if you animate the position and you play this animation, the position is actually going to be driven by the animation and not by the scripting. So you're going to be careful with, so we have to be careful with that and make sure that we just animate the rotation and the scale. Why am I saying rotation? Because rotation is not controlled by scripting, so we can animate that with no problems, but make sure you do not animate the position. So I'm going to click add property here, and you can see that I can select any component from the inspector of my leaves brush to animate, and the scale is under the transform component. So I'm going to expand the transform, and I'm going to click on this plus right to the right of this scale property. There you go. Now I basically have two keyframes, and what a keyframe is basically where a value is defined, and in between two keyframes the value is interpolated. So let's say that the scale and this keyframe was 0, 0, 0, so no scale, and this one it was, let's say, 1, 1, 1. So when I do this, basically when I play the animation, it's going to go from 0, 0, 0 to 1, 1, 1. So this is called interpolation. And as I said, in the keyframe position, the value is actually set. We set a value in the keyframe, and in between keyframes, we interpolate those values. So as I said, we want to create a popping effect. And as you can see, there are already two keyframes, one in the 0 seconds and one at 1 second. So this basically is going to have a second of duration. And roughly at half of this duration, I want to animate the scale. So I already have the scale 2 grabbed here, and I'm gonna just scale it down. And you can see that the scale turns red, which basically means that we are recording the scale. We're saving it as a keyframe. And if you click on this animation again, and if you scroll through this timeline, you can see it plays, right? And just before we end this animation, I want to pop it up just a little bit more than the actual scale. So it goes back to this, and I want to pop it up even further, so it gives this popping effect. So right here, let's say, I want to pop it up. So I'm going to go over 0.2, which is the original scale for the y-axis. And there's already a keyframe saved here, and if I interpolate, you can see that it gives this popping effect, pretty much like if it was launching the apple up again. Alright, so let's just do one more animation, for the idle effect. So basically when there's no particular state being played, we're gonna do the idle state. So to create another animation, I'm gonna stop recording. I'm gonna click on this popping here, and I'm gonna say create new clip. So it's gonna be an independent clip, and this clip is gonna be called idle. And for the idle effect, I want also to deal with the scale. So add property scale, and I'm just gonna scale it up right here. So scale it up. So the idle thing is just this, right? As if it was breathing, even though there's no such thing. Actually, there is such thing, but we can see it like humans do. I don't know. Do you know what I'm talking about? Let's just move on. I'm crazy. So now we have two animations, and if you close this and if you go into the animations folder, you can see that there is a controller that was created. And if you click on the leaves brush, there's actually an animator with this particular controller attached. And what this controller is, this is basically what's gonna drive the animation. If you double click on this, it's gonna open up a new tab, and I'm gonna just drag this into my right to the side of my game tab instead of being at the side of the scenes tab. And here there's actually a state machine. And what a state machine is? A state machine is something that has, a lot of states, and there are transitions in between those states, and these transitions, they have requirements. So let's say a certain condition has to be met for me to go from one state to the other. In this case, a transition is represented by this arrow that connects two of these rectangles, and each of these rectangles is actually an animation slot and is a state. So this entry state and this any state, they're always here. The entry state basically means whenever I start playing this, whenever this mechanism state machine is active, I'm gonna go to the state that's being represented here. So from the entry state, I'm going to go to the popping state. Actually, I don't want this. I want to go from the entry state to the idle state, because this is the idle. This is what's going to play when nothing is happening. So what I need to do to make a transition from the entry state to the idle state is just right click on top of the entry state, make transition, and I'm going to transition to the idle state. There you go. I also want to delete this transition, so right click on it, and it seems like a bug, I don't know, but sometimes we can't delete this one. So what I'm going to do, I'm going to delete the popping state. So just click on it, hit delete. Actually, right click, delete, and then it's gone. So as said, the state machines, they have conditions to go from one state to the other, but in the entry state, there's no condition. It always goes to the state that it points to with no conditions. This is a special case because this is the entry state. We need to tell the mechanism system to go somewhere. In this case, we're telling it to go to this idle state. And in case you press play, you can see this animation playing, right? Because this is the idle state. It's kind of too fast, so I'm gonna go to the animator tab, and I'm gonna change the speed to maybe, I don't know, a third of that. So if I hit play again, this looks way nicer, okay? Alright, so of course, when the apple hits our platform, we want to play that popping animation. So we need to create a transition to this particular state, but we just deleted it, so we're going to create it again. Right click, create state, empty. And this empty state, this is going to be our popping state. So just click on new state here, and we're going to rename it to popping. You can see that the name of the animations are matching the name of our states, even though this is not required. This is just, of course, for I don't know, naming purposes, because it makes sense to call this idle and to call this popping, but I can call it whatever I want. In case I just change, let's say a letter here, I can do this, even though that's okay, that's weird, sorry. Let's go back to popping. So here we need to assign a motion, and motion is just an animation, what's going to be played when this state is active. So we want to play the popping animation, so just drag it here, pretty simple. And we want to create a transition that goes from the idle state to the popping state. So right click on idle, make transition, and just drag it to popping. But when we're done popping, we actually want to go back to the idle state. So we want to create a transition that goes from the popping to the idle state. So right click on popping, make transition, and go back to idle state. As you can see, the arrow points the direction, okay? And when you click on this arrow, you can actually see the conditions that need to be met in order for me to go to the idle, from the idle to the popping state. In this case, there's one special condition that I have to met, and there are parameters for that. I need to, from script, I need to say that there's a property that has to be true or there's actually a trigger that has to be, triggered for me to go from the idle to the popping, because I can't do that without a condition, because there is a condition, and the apple needs to be hitting the platform. So what I'm going to do, I'm going to go into this parameters tab, and I'm going to create a new parameter, clicking on this little plus here, and I'm going to create a trigger. And the trigger is basically something that gets true and then goes back to false. It's basically something that's triggered. It goes to an active state, and then it goes right back to an active state without anyone having to say it to do that. This is the difference between a trigger and a bool. A bool goes to a true state, and it doesn't go back to a false state unless someone told that bool to do that. So we're gonna call this trigger is colliding with apple. So a pretty detailed name. And I'm going to click on the transition that goes from the idle state to the popping state. And here on conditions, I'm going to click on this plus. And basically I want to say that is colliding with apple needs to have been triggered in order for me to do this transition. So I just need to select the trigger, and that's pretty much it. Let's say that you have a floating point value that has to be greater than 10, let's say, for you to create a transition. You just click here, add a floating point value, and let's say, I don't know, random value. So if you want to add this to your transition condition, just click on the transition, click on this plus to add a new condition, select your variable, so random value, and then you can do greater or less. In this case, let's say that I want to do greater. So for this transition to occur, is colliding with apple needs to be triggered, and random value needs to be greater than 10. Okay. We don't know actually how do we set these values, but we're gonna deal with this within a second. Okay, so once I'm playing the popping animation, there's something that's missing here. I need to go back to the idle state. I need to play popping once and then go back to the idle state. But there's no condition for that. I just need to be done playing the popping animation to go back to the idle state. And you don't have to do anything with the transition conditions to do that. You just need to make sure that has exit time is enabled. What this means? This means that this state needs to be completely played before we actually transition. And if you think carefully, this is not true for the idle state. I don't want to have an exit time for the transition from the idle to the popping state. What this means, having an exit time, it means that I'm going to have to play a full idle animation before I move to the popping state, and we might have missed the actual time for the animation. We're just going to leave with this has exit time on, so you can see what does this imply. But that's pretty much it. We have the animation set here. We have the animation also set here. Okay, so now how do I trigger this through scripting? Basically, we need to know where the collision happens and where this have to be triggered. This basically have to be triggered when the apple hits the platform, and all the collisions are dealt within the apple script. So right click on apple, edit script, and in here, inside the else if platform, that means we're colliding with the platform, I want to grab a component from the platform, and that component is the animator component, which is basically what drives the animation playing. So I'm going to go to platform, I'm going to get a component from the platform, which is the animator, and I'm going to say set trigger, and this is basically going to set the trigger to true, so it's going to enable that animation to be played. And the trigger name is colliding with apple. I don't know if the I is capitalized, but it's not. So it's not capitalized. We need to make sure we pass the correct name of the variable, and this should do it. So let's go back to Unity. This, as you can see, it's pretty simple. Just to make sure that you get this, in the leaves bush, this is our platform, there is this animator component, and this is what we're getting, and then we're calling that set trigger function, and this is basically linked with this animator, with this controller. So as you can see, there is such trigger here, there is such parameter that I'm trying to write to. So this is totally this is totally cool, okay? So if I hit play, let's see if I can make this work. And as you can see, it first ends playing the idle animation and then it plays that popping thing. But this is not what I want. This is why I need to disable this has exit time option for the transition between idle and popping. So clicking on this transition, disable has exit time. And trust me, this is gonna save you a lot of time, because when I was dealing with some animations, I didn't know about this, and it was actually a headache until I discovered that I had to disable this has exit time option. So if you hit play again, hopefully this is going to work. There we go. It just needs to be faster, right? So going back to the animator component, go on popping, and you can actually increase the speed, maybe to twice as fast. It's still kind of happening, I don't know, earlier, but it looks nice. It looks nice. And now you know how to deal with Mechanim.